we talked the most basic aspects of kinematics if you want to think about amplitudes really directly in terms of particles rather than in terms of fields. So that was really the basic moving ideas. We really have the scattering of particles. We should think about what a particle is. A particle sort of formally, what sort of formalizes the intuitive notion of what it is. A particle formally is an irreducible representation of the Poincare group. And it has this fundamental property because of Lorentz invariants of being qualitatively different from massless and massive particles. So the summary is that particles are irreps of Poincare. They transform under the little group. And in 4 dimensions, for massless particles, the little group is just a U1, and it's captured by helicity. And for massive particles, it's SU2. So spin. And so amplitudes are not Lorentz tensors, but they're objects that carry little group indices. And so just purely kinematically, if I have an amplitude for a collection of, let's say, just massless particles, then it's labeled by a bunch of momenta and helicities, and they need to have the fundamental property that when you do a Lorentz transformation on the momenta, you pick up a phase factor, the little group factor, on the amplitude. E to the I, 2 theta h for each particle. Similarly, if you have a massive particle, just a single massive particle of spin s is labeled by a 2s index antisymmetric tensor. Okay, so this would just be for a single particle of, let's say, a single particle of spin 1. It would be for that particle, it would have to be a 2-index symmetric tensor. If you have a bunch of them, for each one of them, there would be 2 indices, and it'd be symmetrized in each one. Similarly, that depends on the momenta. Okay, so that's kinematically what amplitudes are. They're not functions of momenta and polarization vectors, or they're only redundantly so. They are they're things that have to transform under the when you Lorentz transform the momenta, they have to pick up the action of the little group. And that's the purpose in life of these Spinor-helicity variables, to make that kinematical fact about the amplitudes obvious. So Spinor-helicity variables, for massless particles, we introduce them, and it's simply the fact that the form momentum being massless means that I can write it as the outer product of 2 two-dimensional vectors. And the Lorentz invariance, first Lorentz invariance is 2 copies of SL2, one for the alpha and the alpha dot index. If we talk about the fully complex Lorentz group, the Lorentz invariants are things that involve contractions of 2 of these guys with the epsilon symbol that will also sometimes abbreviate when there's no confusion. Okay, and so just for massless particles then, if I have a particle that has some helicity h, whatever else there is, and it has its lambda and lambda tilde, say particle A, then this kinematical fact is that when I transform like so, I have to pick up a factor of TA to the negative 2HA multiplied by the same thing. So they have some fixed homogeneity under rescaling. And the homogeneity even tells you what the helicity is. So you don't even have to separately specify what the helicity is. You can just read off the helicity from the homogeneity that it has under this transformation. And if it's a massive particle, what about if it's massive? Well, it's basically exactly the same thing. Oh, sorry. This is just again a reminder from last time, but that way of representing the momentum in terms of lambda, lambda tilde is not unique, because clearly I can take lambda and rescale by lambda t and lambda tilde and rescale by t inverse, and that's exactly the action of the little group. So that's why these variables are important. They're precisely the variables that have the property that when you make a Lorentz transformation on them, they pick up the action of the little group. So the fact that they're not uniquely associated with the momentum is what allows this to be possible. Okay?
This
yes?
is the only non-uniqueness, right?
That's right. That's right. That's right. Exactly. Exactly. Now, what's the analog of this for massive particles? It's completely trivial. Massive particles satisfy that P alpha alpha dot is now rank 2, not rank 1, because it's not massless anymore. So that means that I can write it as the sum of the outer product of 2 vectors. So, very dumbly, lambda tilde alpha 1 plus lambda alpha 2, lambda tilde alpha dot 2. But we can just write this as lambda lambda tilde with an additional I index, where I now runs from 1 to 2. And once again, this is not unique because I can take any lambda I and do a 2 by 2 transformation on this capital I index. And if I do the opposite, as usual, since it has a downstairs index, then P goes to P. Okay? And that's precisely the action of the SU2 little group on for massive particles. Okay? So this is exactly the action of the SU2 little group. So now our life is really easy, because if we have massless particles or even massive particles, now if I have a massive particle, I have to make a 2s antisymmetric tensor out of the lambdas of that guy, lambdas and lambda tildes of that guy. So I have to make some expression that has 2s indices upstairs and symmetrize in those indices. If I have a bunch of massless particles, they still have helicity. So if it's massive, they have this extra I index. If it's massless, they don't. And that's it. Okay, so I just have to make something with the right homogeneity under rescaling lambda and lambda tilde for the massless ones, and the correct number of indices appropriately symmetrized for the massive ones. Okay? Any questions about this? This is utterly trivial. This is absolutely utterly trivial. But what we've done is do the responsible thing. Right? We're now talking about the amplitudes in a way that the symmetry is as obvious as possible. Okay? So, yes. Oh, I'm sorry. Here? Which ones can't you read?
On that side of the sorry, where your hand is. I don't know my left and right.
Oh, here. So this is J.
Yes.
Yeah.
And below?
This one, oh, it's not a J. That's why you can't read it. You shouldn't be so polite. Next time, say the equation is wrong. Don't say I can't read it. You see, you just slowed us down by a factor of 3. Come on now. Jesus Christ. All right, any other questions? All right, very good.
Nima?
Yes?
So this is defined up to multiplication by some unknown Lorentz scalar, right?
No. This is just the kinematic. I haven't told you how to determine the amplitude. I'm saying that any amplitude has to be some object like this.
Yes.
We're now going to talk about how to determine it. Now, just so it's not so abstract, let me give you some examples of what some familiar amplitudes look like.
Nima,
Yes.
what about the Maxwell condition for the lambda?
Oh, I'm sorry. Thank you. Yeah. So now we have to say something about. Sorry.
Can you repeat
Thank
the
you.
question?
Yeah. So we have to say what the mass is. So p squared equals m squared means that the determinant of this p alpha alpha dot is equal to m squared, and that means that I can take, if I take 2 of these lambdas and I contract their I index, okay, then I will get m epsilon alpha beta. Okay, and similarly, if I take 2 of the lambda tildes and I contract their I index, I will get m epsilon alpha dot beta dot. Actually, it doesn't quite mean that, because in principle I could have an m and an m tilde here. All I know is that the product of the m and the m tilde is equal to m squared, but It doesn't matter. I'm just going to, ahead of time, choose a normalization for them so that they're both equal to a m. This is an important point because it means that I do not have the little group freedom to rephase the lambda and the lambda tilde. That's not part of the little group because that would change the determinant. Okay? That's right. Exactly. Exactly. Okay? Okay, and so, for instance, this means various things. For instance, there's a formula like P alpha alpha dot lambda alpha I. What is this equal to? So this is something with an upstairs I index, a downstairs alpha dot index. So this is just m lambda tilde alpha dot I. Okay, so I can go back and forth between lambda and lambda tilde in this way. Also, of course, the other way, P alpha alpha dot lambda tilde alpha dot I. Maybe there's a minus sign here, I think, just by the conventions for how we define things. Okay, so what is the name of these equations? But what's another name for these equations? This is the Dirac equation. Okay, except we're not talking about the gamma matrices or anything. As I promised, we're not going to see a single gamma matrix. Don't. Okay, so I hate gamma matrices. So yeah. No. It's just the Dirac equation by itself. You later have to say that the thing you're talking about is a Grassmann field. Just as an equation, this is the Dirac equation. It's just the Anschauer. It's the Anschauer equation of motion. All right, but let me give you some examples of what some familiar amplitudes look like, just so we get some practice. So first, so let's look at, for example, so we're not deriving anything, I'm just telling you what the answers look like, just so you see what the kinematics looks like. So let's do some massless examples. So let's say I'm talking about what example do I want to do? Yeah, let me write down a few that I'll use later. So yeah, let's say I'm talking about Compton scattering, but massless Compton scattering for massless electron. Okay, the massless electron Compton scattering is so for this. At tree level, of course. So 1 minus fermion minus a half, photon of helicity 2 plus, 3 minus, and 4 plus a half. So this is 1, 3, 2, 4, 2, so that's what the amplitude looks like. And let's just, again, this is just for practice, so we can see particle 1 has helicity minus 1 because when I scale 1 to t1 times 1, I just pick up a factor of t1. Okay, there. Similarly, 3 has, particle 3 occurs twice with the angle bracket, so that's why it's a photon of helicity minus 1, and so on.
What is
Okay?
I don't understand the brackets you wrote. There's a 1, 3, I understand, 2, 4, I understand,
Yes.
and then there's...
This guy is like, so this is like lambda tilde 2 alpha dot. Let's say this term is P1 alpha alpha dot lambda 3 alpha. So the only way they can contract with each other. If I wanted to write it purely in terms of the Spinor-helicity variables, I can. Sometimes I'll slip up and just write them in terms of the p's. This would also be, this first term would also be 2, 1, 1, 3, for example,
Where
like
did
that.
4 disappear, or is that not...
Sorry, no, this is one term, and then there's minus the same thing with 4, 1 to 4. So I could also write this like this, minus 2, 4, 4, 3. Okay? All right, so that's one example. So this is massless electron Compton. In fact, there's a very nice formula for any spin. So if I have massless particles of any spin here, if I put 1 minus s and 4 plus s, it's exactly the same formula, but this factor is to the power of 2s, And this factor is to the power of 2 minus 2s. Okay, so that's a very beautiful result. Now, notice there's something slightly interesting about this formula. We'll come back to this later. But there's a variety of interesting things about this formula that we'll come back to later. Actually, I won't give it away now. This is just so we see a few examples. Okay, here's another example. Graviton-graviton scattering. Okay. Again, at tree level, but let's say I have 1 minus, 2 plus, 3 minus, 4 plus. These are now all gravitons. This formula is 1, 3, 2, 4, all to the 4th, divided by s times t times u. Okay, now let me write down an example of something involving a massive particle and some massless particles. So let's do like massive Compton scattering.
You didn't explain how to get...
No, I'm just writing down,
But the Mandelstam, we did not explain at all, right? These are just like...
Well, I mean, how many people don't know what a Mandelstam variable is?
I know what it is.
Yeah.
I'm not asking, how did you know that this is s times t times u and not st squared?
Oh, I haven't explained. We're going to derive this in a moment. I'm just writing down examples of what the formulas look like, just so you see what they look like. Okay, I'm not, and this is just meant to get some practice to see how, again, from here you can check and see that particle 1 has helicity minus 2. Because when you rescale 1, you pick up a factor t1 to the 4th, and that tells you that it has helicity minus 2. Okay, we're going to come back and derive these things and more, and there's a lot to say about the physics. Okay, so here's massive Compton scattering. And, I forgot, there's some overall coupling constants. So there's some E squared, there's some 1 over m Planck squared. I'm not going to be careful about the overall coupling constants sometimes. But here, again, we're going to have an E squared over s minus m squared times u minus m squared. And then let me just write down in one shot the formula for spin 0, 1/2, and 1 Compton scattering. So here it is. It's factors that we've seen a moment ago. Now we're going to get something new, and I'll explain the notation in a second. This is for spin 0. Massive particles of spin 0, massive particles of spin 1/2, massive particles of spin 1. Okay, now, what is the notation here? Remember, when it's a massive particle, I need to have a 2s symmetric tensor. So each guy, I have to have 2s of them. Now, but precisely because it's symmetrized, I mean, what I should do, for example, here, like let's say in this example, I really should tell you, since particle 1 has spin 1, I should have some tensor with 2 upstairs indices, which are its SU2 index. So I should have something like a lambda 1 with a capital I1 and another lambda 1 with an I2, and I'm symmetrizing in these indices. And then the rest of the indices will contract in some other way, but I have to symmetrize in these indices, right? Now here's a nice bit of notation. Precisely because we're symmetrizing them, there's no point in writing down the indices. I can equally just write down lambda 1 squared, because I know what I'm supposed to do with it. I'm supposed to put indices and symmetrize them. So in this way, the expressions look identical between the massless and the massive cases. Okay? It's just that you have to remember that the massive guys have an index on them. So when you're doing it in tech, you write it in bold. When you do it on the blackboard, you put an underline. And the underline just reminds you that the underlined ones are the massive particles, and there's really a tensor index that's going along with them, and everything is going to be symmetrized. Okay, so now I want you to look at this expression.
But you only symmetrize when it's the same particle, right?
Yes, that's right. It's only symmetrized for the same particle. And it's completely unambiguous. So once you write down the expression, it's totally unambiguous what you mean by it. So I want you to look, so here are a few examples, and now let me comment on some features of the physics that we're going to be talking a lot about. So already back in these examples with just massless particles, These are interesting scattering amplitudes in, maybe we could have done the most trivial example of all, which is just phi cube theory, massless phi cube theory, right? So what would the amplitude in massless phi cube theory be? Massless or massive, it doesn't even matter, but let's say we're doing massless phi cube. It would be something like g squared 1 over s plus 1 over t plus 1 over u. Just sort of trivially what you get from Feynman diagrams. Okay. So let's now make a few comments about what these amplitudes. First, the most trivial thing is that they're very simple looking. Okay? There's no u bars and v's in the Compton case, right? There's no Dirac algebra to do. We've just written down the whole answer. Now, in the spin 1 case, there's no polarization vectors anywhere. Of course, there should not be any polarization vectors anywhere. That was the whole point. Furthermore, you see some sort of patterns that may not have been obvious to you ahead of time. You see, this spin 1 guy, numerator, is just a square of this sucker that you saw for the spin 1/2. It's not obvious ahead of time, right? Certainly not obvious from the Feynman rules or just playing around. Okay? And this is the final answer. So you've finally seen the Compton amplitude. You've never seen it in your life before. Okay? You've seen it with a polarization vector. Okay? Even on the photon side, never mind on the massive W side, like this example. Okay, so yeah.
What are the two lines? Like there's like, I mean, the left. What is this?
That's the same thing that we talked about here. That's
I'm asking, like,
right.
What does it multiply? Why is it
the whole thing is multiplying 1 over s minus m squared, 1 over u minus m squared. Okay, so that
it multiplies both the two lines, or just
yes, it's multiplying everything. These are the numerators for all of these expressions. Okay, right. Yeah, it might be easier to look at the actual blackboard. Anyway, okay. So, all right. So that's one comment. Now, a more interesting comment is look at this expression for phi cubed. See, phi cubed theory looks like the amplitude looks like the sum over 3 channels: 1 over s plus 1 over t plus 1 over u. That's exactly what's reflected in the Feynman diagrams. You get the s channel, the t channel, and the u channel diagrams, right? But notice something interesting about both. Let's say, this massless Compton amplitude, okay, involving photons. Here, the amplitude does not look like the sum over channels. In fact, it has a product of s and u downstairs, not a sum. Even more extreme for gravity, it has the product of st and u downstairs, not the sum. Okay? And this, in fact, is the most invariant sense that we see directly in the structure of the final answer. For the amplitudes, why it is that if you're going to use Lagrangians to describe theories of massless spin 1 and massless spin 2, you have a difficulty, and you have to introduce gauge redundancy or something, because, in fact, the actual answer does not look like the sum over channels. So what happens when we use Feynman diagrams? What do you think happens when we use Feynman diagrams? There, like if I do Compton scattering, it is the sum over channels, right? I get the s channel and the u channel. And maybe even there is a contact term. So that appears to write as a sum over poles. Here it's clearly manifestly impossible to split this up into the sum of something over s plus something over u. So what's going on? Each term by itself isn't a Lorentz invariant object. Each term by itself has these crappy polarization vectors in it, which remember are not invariant things. Okay? So each term isn't Lorentz invariant. And in fact, if we wanted to, we could split this into something over s plus something over u, provided that we break Lorentz invariance, and the expression that we get in that way would match what could match, for example, what we got from Feynman diagrams in a light cone gauge or something like that. Okay? But the actual answer does not want to look like the sum over channels. That's a deep fact, and it's a deep difference between theories of massless spin 1 and massless spin 2 particles and stupid theories, simpler theories that don't have any such structure in them. Okay, so that's one comment. We see that even here, it has, even when the particles are massive, what really matters is the photons and the gravitons. Okay, even when it's massive, it's the product of the poles in the s and the u channels, and not the sum.
Nima?
Yes.
In this formulation, we do not write down the Lagrangian.
That's right.
So
I have not told you where I'm getting this amplitude yet. So yeah.
I understand.
Yeah.
But in this formulation, how do you see that this is a sixth theory?
What is a Sick theory?
Phi cubed.
Oh, well, there's not a Sick theory in perturbation theory. There's nothing wrong with it in perturbation theory.
So how do you see that it is a sixth theory if you don't have a Lagrangian?
well, you would, maybe let's talk about this question. I mean, there's so many other questions before we get to that one, but you would have to see eventually the need for the non-perturbative effects that tell you that the theory is unstable, right? But to try to understand from the on-shell point of view why you need those non-perturbative effects is a very interesting open problem, so it's
no simple answer.
I don't have a simple answer from the on-shell, but as I said, there are so many simpler versions of this question before that I would that we could talk about the other ones first. Okay, so all right, so the final comment is to make is this. So we have this feeling that when you take the high energy limit for scattering amplitudes involving massive particles, whatever they are, that in the high energy limit, you should see them turn into the constituent massless particles that make them up. But there are more degrees of freedom for the massless, as we've discussed, there are more degrees of freedom for the massive particle than the massless one. So how do we see that? How do we see the high energy limit? And how do we see in the high energy limit that the massive particles contain all these different helicity massless particles? Okay, now if you know anything, if you've done this exercise in the standard model in deriving the equivalence theorem, it's a pain in the ass to extract the longitudinal component to the polarization vectors for massive particles and extract them compared to the transverse ones and so on. What's going on in this formalism? Well, let's look at this answer. Let's say for the spin 1 particle. And if you just look at it for a second, it seems to violate one of the rules that I told you about. It looks like I'm writing down something involving, you see here 3 is occurring as a square bracket, whereas here 3 is occurring as an angle bracket. So naively, remember, if these were massless helicities, I'm not allowed to add expressions with different helicity weights. Okay? Now remember, when they're massive, I don't have that helicity symmetry. I only have the SU2 instead. So this is a perfectly legal expression for massive particles. All right? So given that clue, how do you think I take this formula and I extract the high energy limit and see all the different helicity components? What do you think taking the high energy limit is? You just remove the underlines. That's it. See, when you remove the underlines and now you expand it out, now it has many terms. It has 3 terms. One of them has particle 1 with helicity -1 and particle 3 with helicity +1. The other one has it the other way around. And the cross term is the spin 0 longitudinal component. Okay? So the act of taking the high energy limit is unbolding or removing the underlines. Okay, and that's the sort of trivial way in which you match from low to high energies. At least that's true in any expression that doesn't have some kind of sickness as m goes to 0. Okay, so that in any expression that's smooth as m goes to 0, which will be true for the final amplitude for any sensible theory, it'll have that property, and that's how we can see that the massive amplitudes contain the massless ones. Let me make a final comment. Let's go back to this amplitude. I said that we can see that this is what the answer looks like. Now, the fact that this has poles as s and u goes to 0, okay, that makes sense. But notice that if I make this spin bigger and bigger, starting at spin 3/2, this is going to have this funny factor downstairs. Now, that funny factor downstairs is not a pole that a 2 to 2 amplitude is allowed to have. 2 to 2 amplitude can only have poles as s or t or u goes to 0, not this funny combination. Right? So that actually tells you this formula is nonsense. The second the spin gets bigger, greater than or equal to 3/2. And that's in fact correct. There are no consistent interacting theories for massless particles, charged massless particles of spin 3/2 or higher. And that's how we...
Why nonsense?
Well, because we'll review this, that is going to be the whole point that we're going to talk about in a second, but the 2 to 2 amplitudes are only allowed to have poles when s or t or u go to 0. This is not s or t or u. This is some funny combination. Okay? It's not s or t or u. And so this expression ceases to make sense when s gets bigger than 3/2. So we're actually going to learn in a moment what the allowed consistent theories of massless particles are. We're going to learn it, in a half hour worth of algebraic analysis, very, very quickly, but this is one of the things that we'll see, that simply requiring the correct kinds of poles and factorization on the pole is going to exclude immediately huge chunks of theories and just leave us with the theories that we know and love. If I wrote down the analogous formula for gravity-Compton scattering, there would be an STU downstairs, there would be a 4 minus 2s upstairs, and I would come up with the same conclusion for particles, particles of spin 5/2 or higher. Okay? And so the simple existence of gravity makes it impossible to have massless particles of spin 5/2 or higher in nature. Okay? The simple existence of photons make it impossible to have massless charged particles of spin 3/2 and higher. Sorry? Massive are okay, and then, but something funny should happen to them, obviously, because the massless limit shouldn't be smooth. So the extension of this argument is why we can't have appropriately defined notion of elementary particles, which are massive, but which have spin bigger than, greater than or equal to 3/2 or greater than or equal to 5/2 with a large gap to where other charged or massive particles might be. Nope. Nope. No. So, well, that's the fact there's no similar statement for spin 0 is also known as the hierarchy problem. Okay. All right. So, well done. All right. Now let me just give one more example, not just so you see we can do like weirdo-looking amplitudes. So let's say I have a massive particle of 1, 2, 3, and 4. I don't know. This is spin 1/2 particle, massive spin 1/2, top quark, KK graviton. Well, that's not a massless gravitino in the real world, but anyway. So, okay. So let's say I have something like this. Then again, there are many expressions I can write down, but here's one sort of contact term, just a polynomial, just again to illustrate. Just the formalism. Okay, so that's an expression. Okay, so you see that it has particle 2 has a total of 4 indices. Okay, so that's good. It's supposed to be a spin 2s, a rank 2s tensor. 3 has the correct weights, positive 3/2. 1 has the correct weight. So that's a candidate expression for an amplitude involving these guys. Okay, so much for kinematics. Any question, and some clue of the interesting sort of structures that we're going to be seeing. But any questions about this so far? Okay, so now we're going to start getting a little more systematic. Okay, so the first thing we're going to talk about, and by the way, I'm doing this first of all because this is the systematic way of building things up for amplitudes, but we're going to copy every one of these steps. We might not have time to do them all in detail, but when you see how all of this works for amplitudes, you will know exactly what we're doing for cosmology when we do that tomorrow. Okay, we're going to do every single one of these things exactly the same way. Okay, so and in fact, as I'll stress next time, as I'll stress tomorrow, the objects we're going to talk about in cosmology are going to contain the formulas are going to contain the formulas we're talking about in amplitudes. There's a special case. So they're not just roughly related. One properly generalizes the other, strictly generalizes the other. Okay, so you really need to understand this. It's very beautiful and important by itself, but it's also going to be the sort of the template for what we're going to do to thinking about cosmology without time tomorrow. Okay, so our first exercise is going to be to understand 3 particle amplitudes. And we're going to do this for massless particles to begin with, where it's shockingly constraining. Now, you might be a little bit confused because you probably have not computed 3 particle amplitudes in your courses, and for massless particles especially. And there's a good reason for it, because most 3 particle amplitudes that you might compute, let's say in Yang-Mills theory or in gravity, if you were to compute them in your courses, you'd get 0. Okay, so we'll see why you get 0 in a moment. But again, that's something else that maybe it struck you as funny when you're learning the subject for the first time, that clearly these cubic vertices are the most important things, and yet somehow the first thing you talk about are 2 to 2. Okay, so there's actually, the cubic vertices are directly associated with on-shell amplitudes, and we're going to understand exactly how that works. But just to stress what the, why it is that they should be so incredibly constrained, let's just imagine something very simple, like I have 3 scalars, 3 spin 0 particles. Now, what could the 3-particle amplitude possibly be? Even if you don't think about anything to do with anything fancy. It just has to depend on 3 momenta. There's no spin, nothing. 3 momenta, P1, P2, P3. What could it be? Sorry? Yeah, it could be a constant. So some constant. But can it depend on the momenta in any way? It can't. Why not? Because every single Lorentz invariant is 0. Right? Like, what is P1 dot P2? Well, that's P1 plus P2 squared. But that's P3 squared, and that's 0. Every single Lorentz invariant is 0 for 3-particle kinematics. That's unlike 2 to 2 scattering, where we have 2 Lorentz invariants. We have S and T, right? Or ST and U with S plus T plus U equals 0. So here, purely from symmetries, I could have any old function of S and T as the amplitude, but for 3 points, nothing, just a constant. Okay? Now let's just keep on going a little bit. We're not going to pursue this way of talking about things, but just so you see. Let's say I want to do something like I have 2 spin 0 particles and 1 spin s particle. Okay? And let's say this spin s particle has, I'm going to talk about it in standard language now. So it's a polarization vector, so it has epsilon mu1 through mu s. Okay? Once again, what could I possibly write down? Only involving the momenta, there's nothing I can do, right? But I somehow have to contract into this epsilon index. And I have to get rid of these epsilon, these indices on mu, so I have to contract something into it. Remember, epsilon mu, its p, so if this is particle 3, its p mu is equal to 0. Okay? So what could I contract for each one of these guys? Well, it could be some linear combination, alpha p1 mu, beta p2 mu, gamma p3 mu. That's what I could contract into one of these indices, right? But p3 gives me 0, and p1 plus p2 is equal to p3, so that gives me 0. It's equal to minus p3. So the only combination that gives me something non-zero is p1 minus p2. And therefore, we also see that this is just showing you that the answer is just pure spin, is completely determined by spin. In this case, up to an overall coupling, all it can be is p1 minus p2 mu1, p1 minus p2 mu s, epsilon mu1 through mu s. Okay, we'll see this in nicer Spinor-helicity language in a little bit. But this is just to see in these simple, familiar examples that things are, there is no room to depend on anything. Once you give the spins, the answer is completely fixed. Let's go back here for a second, just so we're clear on this point. You might be slightly confused. I mean, it's true that if I write down phi cubed, that phi cubed gives me this Feynman rule, a constant. But naively, there's all kinds of operators I could write down, like d mu phi, phi. That's another operator. Or I could put more and more derivatives, boxes. Okay? This analysis is telling us something ahead of time. All of those things are going to equal a constant when it comes to evaluating the 3-particle amplitude. And of course they do, because all those derivatives just turn into the momenta. When they contract into each other, they give me 0. Or they give me the particle mass, or whatever. Okay? So this is a very sort of primitive place where you see the usefulness of the on-shell way of thinking, because you don't have to worry about equations of motion and field redefinitions and all that kind of crap that you have to worry about when you write down local operators. Okay? The actual invariant is captured by the amplitude, and so you just better write down the amplitude directly. You don't need to worry about what the Lagrangian is. You can just write down the amplitude directly. In this case especially, where the answer is going to, as we see, is going to be completely fixed by symmetries, by Poincare symmetry. Okay, But now let's do this more systematically. And to do it, the first thing that I want to do is tell you how to think about momentum conservation in general in this language. Switching. Oh, that's worse. My pen here is kind of collapsing, so let's try this one. Oh, all right. Was there one on, huh? This one? Oh, this one. All right, let's talk about momentum conservation. Oh, that's a little better. So let's say I have n massless particles. So n massless particles. So momentum conservation is a statement that sum over A, PA alpha alpha dot is equal to 0. So that's that the sum over A, lambda tilde A is equal to 0. All right, and now I want to think about this in a slightly different way. Actually, to begin with, I want to think about what the data is that labels these scattering particles. The data is giving me these lambdas and these lambda tildes. So how do I give the data for the scattering particles? Well, I have to give me lambda 1 through lambda n. So literally, lambda 1 is some two-dimensional vector, a1, b1. Lambda 2 is some two-dimensional vector, a2, b2, up to an, bn. Okay? So the data in specifying the lambda is a 2 by n matrix. Now, the way that I've presented it, you think about this 2 by n matrix as n two-dimensional vectors. But let's now think about it as two n-dimensional vectors instead. So I'm going to think about it as two row vectors instead of n column vectors. So this is now in some funny n-dimensional space. Here's some giant vector A and some other giant vector B. Okay? Now, what happens if you go to a different Lorentz frame? Remember, Lorentz transformations act like a 2 by 2 linear transformation, right, on lambda. So each one of these guys is going to get acted on by a 2 by 2 linear transformation. So in a different Lorentz frame, I'm not going to have the same A and the B. I'm going to have some different A prime and some different B prime. So A and B are not a good Lorentz invariant way of talking about what the data is, right? But is there something Lorentz invariant here? Can you see something that is Lorentz invariant in this picture? I have this A and this B vector in an n-dimensional space. I do a 2 by 2 linear transformation, I get some A prime B prime, where A prime B prime are some linear combination of the old A and B. So what do you think is fixed? Huh? Not A times B, no. A times B doesn't mean anything. These are vectors. Sorry? You know, maybe the professor in the room is not the one who should give the answer, but yes. Forget about one of the professors in the room anyway. Hopefully no one heard what he said. So what?
Multiplication is not, I mean, is
A dot B is not invariant. A dot B is most certainly not invariant under a linear transformation. What is invariant? A wedge B is much closer, exactly, and is basically correct. A wedge B, but said slightly more in a way that someone in grade 4 might understand. The plane. There's a plane that's spanned by A and B. There's a two-dimensional plane, and in a different basis, the two-dimensional plane is the same. This is really cool. The Lorentz invariant way of talking about the data is to give me a certain two-plane in n dimensions. Right? So I'm not going to be talking at all about fancy schmancy stuff, but if you want some sort of clue for the beginning of fancy schmancy stuff like Grassmannians and so on in this subject, it starts here. That just thinking about the data forces you to talk about a two-plane in n dimensions. So here there's a two-plane I could call capital lambda in n dimensions. And that's the Lorentz invariant information about the lambdas. Now, there's another two-plane lambda tilde. Okay? And now I've drawn them this way deliberately. They're orthogonal to each other. Why have they drawn them that they're orthogonal to each other? That's momentum conservation, right? Momentum conservation is the statement about the dot product now, right? Momentum conservation says if you take the sum over A, lambda tilde A, alpha alpha dot is equal to 0. That means if you take any vector in the lambda plane and dot it with any vector in the lambda tilde plane, you get 0. Okay, so these two planes are orthogonal to each other. All right, so that's what the data of a scattering process is. It's two planes in n dimensions that are orthogonal to each other. That's the Lorentz invariant way of talking about it. Okay? That's true for any number of particles, but now let's specialize to the case of 3 particles. Okay, if I specialize to the case of 3 particles, and by the way, we could have derived this result algebraically in 30 seconds without going through the song and dance, but I find this a much easier way of thinking about it and remembering it, and it tells you more about what's going on. So let's say I have a 2-plane, but now I'm in n equals 3 dimensions. Now you see there's a little problem. I have to have a 2-plane lambda, another 2-plane lambda tilde. They both have to be orthogonal to each other. There's no such thing in 3 dimensions. If you give me a generic 2-plane lambda, there's just a normal vector to it. So that tells me that the lambda tilde plane has got to actually have collapsed to a line. So that's cool. It tells me that if the lambdas are generic, lambda tilde 1, lambda tilde 2, and lambda tilde 3 all have to be parallel to each other. Okay, so either the lambdas are parallel and lambda tilde 1 is proportional to lambda tilde 2 is proportional to lambda tilde 3, or the other way around. Okay? Or I can have lambda tilde generic and the lambdas parallel to each other. Okay, so that's what's special about 3-particle kinematics. This also immediately explains why all the invariants are 0. Because remember, all the Lorentz invariants, like P1 dot P2, is the angle bracket times the square bracket. And so in any one of these configurations, let's say in this configuration, the lambdas are generic, but the lambda tildes are parallel to each other, so they contract to 0. I'm contracting the same thing with itself with the epsilon symbol, so I get 0. So in this configuration, all the square brackets are 0. In this configuration, all the angle brackets are 0. So all of these invariants are 0, which of course we knew anyway, but we can sort of interpret now from this picture. Now you can also see why there is something peculiar about 3-particle amplitudes in Minkowski space. Okay? Because there's something further special about Minkowski space. Remember, in Minkowski space, in other words, in 3-1 signature, lambda tilde had to equal lambda star. So that means that in Minkowski space, if the lambda tildes are parallel, then the lambdas also have to be parallel to each other. Okay? So it's an even more degenerate configuration. And this is what you're used to talking about. When you say, when you have a massless particle, if it splits into 2 other massless particles, they have to be going in exactly the same direction of motion, and you just share the energies. Right? It's a completely singular collinear splitting. And that's simply a fact about life in Minkowski space. It's not true for general complex momenta. There's a more generic situation for general complex momenta or for real momenta, but real momenta that are not in Minkowski space. If we work in 2,2 signature, then we can have the lambdas and lambda tildes real, but then they're simply independent, and we don't have this conjugation condition. Yes?
I lost you. How did you
Yes.
conclude that they are parallel?
Oh, so you remember, I have to have the general situation in n dimensions is that I have to have two planes that are parallel to each other, that are perpendicular. Now let's go to 3 dimensions.
And then I thought you would say, oh, it's imaginary, 6 dimensions.
No, nothing is imaginary. nothing is imaginary. No. It's just that in 3 dimensions, you can't do it. You have a plane. I can't have another 2 dimensions that are parallel to it, that are perpendicular to it. I only have one direction that's perpendicular to a plane in 3 dimensions. Okay? So if the lambdas are generic, so they give me a full 2-plane, the lambda tildes have got to be parallel to each other.
But
Okay.
when you were talking about this
That's right. That's right. That's right. Yes.
So that way you always have two vectors in the domain, why not three?
No. It's so I'm saying that the information about the that the lambda tilde 2 plane has collapsed to a line. I mean, I'm just sort of drawing it, just so there are many ways of drawing it, but lambda tilde, all the lambda tildes have to be parallel to each other, and that's and when the lambda tildes are parallel to each other, I don't actually get I don't get a two-dimensional space spanned by them. I only get a one-dimensional space spanned by them. Okay.
The lambdas are complex, right?
Yes. So so here's a very useful thing. You can draw these pictures and just think about them as real, and you'll never make a mistake. Okay? You'll never make a mistake. And doing that is effectively doing everything in 2,2 signature. And because all the answers at this level are analytic anyway, you get the correct answer in any place you can get the correct answer. Okay? So it's really useful to visualize them as real. When you visualize them as real, you're secretly doing things in 2,2 signature. Okay? But you're getting the correct answer. All right, so that's what's special about the three-particle kinematics. But now let's talk about what the three-particle amplitudes are. The three-point amplitudes. So now the answer will depend on which one of these configurations I'm in. But conventionally, we'll sometimes draw with a black vertex the situation where the lambda tildes are parallel to each other. That's just to remind us. And a white vertex, the other one, this is the blue vertex, I guess. Okay, but let's say we're in this situation. Then what could the amplitude look like? Just depends on 1, 2, and 3. Well, it can't depend on the lambda tildes because they're all parallel to each other. So what I get, the only thing I can get is 1, 2 to some power, 2, 3 to some power, 3, 1 to some power. That's it. Now I can determine what the powers are by, and some coupling constant. I can determine what the powers are just by the helicities of the particles. For example, what is the helicity of particle 1? I have to learn that A plus C is equal to minus 2H1. Similarly, A plus B is equal to minus 2H2, and B plus C is equal to minus 2H3. So that's 3 equations and 3 unknowns, and I solve for the amplitude. So I'm done. No Lagrangian, no thinking.
How do you know
Right?
there is no denominator?
Oh, there will be denominators. In fact, the denominators are going to be a huge part of the drama in a moment. Okay, but if we have general H1, H2, and H3, and we're in this situation where the lambda tildes are parallel, then we can have some G 1, 2 to the 1, 2 to the H3 minus H1 minus H2, 2, 3 to the H1 minus H2 minus H3, 3, 1 to the H2 minus H3 minus H1.
You already
Okay.
kind of solved the, inputted the system of equations?
Yeah, I just solved these 3 equations and 3 unknowns for the helicities. Okay, so you give me these helicities, that's what the answer is. In the other situation, in this situation, there's some G tilde. I don't know it's the same as G. Maybe it is, maybe it isn't. And I get this guy. But now the other way, H1 plus H2 minus H3. Okay? And so we have determined purely from symmetries what the 3-particle amplitudes are. Yes?
Is there like a deep reason why this kind of looks like a CFT?
Yes, and we'll first the argument is essentially identical to the argument that the structure of the 3-point functions in CFTs are locked by conformal symmetry. And when we talk about the relationship between the amplitudes and correlation functions in cosmology, or in ADS for that matter, the two things become identified. Okay? Nothing. This is now reversed. So this is h1 plus h2 minus h3. And in this case, this is where the lambdas are parallel. So you remember either the lambda tildes are parallel or the lambdas are parallel. If lambda tildes are parallel, the answer can only depend on lambda, and the other way around. Okay, so let's look at some examples. So that's what it can look like in general. So let's look at some examples. Let me jump to an interesting one. So let's say I have particles of spin s, and I'm going to look at an amplitude where it's minus s, and plus s. Okay? Now, what could I get? What could I get from here? Well, in this configuration, I could get 1, 2 cubed over 1, 3, 2, 3 to the power of s. That's what I could get if the lambdas are parallel, if the lambda tildes are parallel. And I could get the other way around, 1, 2 cubed over 1, 3, 2, 3 to the negative s if the lambdas are parallel. That's just what I get from that formula. Okay, good. Now, in fact, only one of these is consistent. And to see the one that we want, let's see what happens when we go back to Minkowski space. Okay? As we go back to Minkowski space, remember, the lambda tildes are already parallel. So if we're going to go to Minkowski space, that means the lambdas are also going to become parallel. That means that all these brackets are vanishing. And so now in this configuration, the whole thing will go to 0. In this configuration, the whole thing will diverge. Okay? And so we don't use that one. Okay? So the requirement that you have a smooth answer in Minkowski space picks out this one. Okay? No, it's not, but it's 0 in Minkowski space. Exactly. It's 0 in Minkowski space, but it's not 0 away from Minkowski space. In fact, the formula ends up being, in general, that the amplitude is equal to this when h1 plus h2 plus h3 is negative, and it's equal to this when h1 plus h2 plus h3 is positive. By exactly this requirement. Now, what about the case where h1 plus h2 plus h3 is 0? Okay, that includes the case where everything's a scalar. Okay, that's fine because the amplitude is just a constant. It doesn't depend on any of these things. The other cases are interesting. So let's do another example. So let's look at a.
That when h1 plus h2 plus whatever is 0, what is the answer?
Well, when h1 plus h2 plus h3 is 0, we appear to have an ambiguity because either one. So let's just do an example. So let's say I have a scalar and 2 negative helicity fermions. This is a Yukawa coupling, a normal Yukawa coupling. And if this is 1 and 2, what is the amplitude? It's just 1, 2. Some y, 1, 2. Right? Beautiful. Okay? But there's something else that I could write down purely at this level, minus a half plus a half. Now h1 plus h2 plus h3 is 0, right? And here the expression that I could write down is 1, 3 over 2, 3. Or I could write down the other one. Or I could ultimately I could write down 2, 3 over 1, 3. So I could have a g plus g tilde here. This is all bad because this is not, we don't know. We don't have a name for this guy. See, so already we're seeing that we can get out of this things that we don't get from Lagrangian. Right? There's no Lagrangian that gives you this 3-point amplitude. But we can write it down in principle. We're momentarily going to see, or I'm going to tell you the structure of the argument, that actually says that while it's perfectly legitimate to write down these 3-particle amplitudes, and we've written down 3-particle amplitudes for any spin 17 million, anything. In a moment, we're going to set up the physical problem of consistency of 4-particle scattering. And that's going to be poles in the correct place and factorization. And that is going to rule out almost all theories, other than the theories that we know and love. Okay? And in particular, it will rule out these guys. So these guys are actually also illegal. They're just forced to be 0. These 3-particle amplitudes cannot exist. Okay? Yes?
How do you know what to put in the denominator?
Oh, it's just coming from this formula. I did nothing but apply this formula. Okay? Everything is completely fixed. There's no guessing here, right? All right? All right, so now we know what the 3 particle amplitudes are, and so you're supposed to be impressed by this, right? Because we've not written down any Lagrangians, we haven't done anything, so you can show some appreciation. Wow, so cool. Thank you. God thanks you. I'm just a messenger. Such a dangerous thing to say in the city, So not cool. I'm so sorry. No. I'm going to Guantanamo the second I get home. There's no doubt about it. Yeah, that's what I said. That's what I said. What am I? Not enough sleep. All right, very good. All right, let's look at some of these examples again. So let's look at, again, phi cubed is just boring. It's just G. We had this nice Yukawa, minus a half plus a half. This was some y 1, 2. Then we have Yang-Mills. This was like minus plus, let's say. And this guy was G 1, 2 cubed over 1, 3, 2, 3. And let's do gravity. Also minus plus. And this is some kappa, or 1 over m Planck, times 1, 2 cubed over 1, 3, 2, 3, all squared. All right, and I want to make a few comments about this. First of all, units. The units of the 3 particle amplitude is mass. Okay, the easiest way to remember is just what it is for phi cubed. Okay, so the units are mass. And so from here we discover G as units of mass. Y is dimensionless. That's good. The Yukawa coupling is dimensionless because 1, 2 has units of momentum the same as mass. G is dimensionless. Good, that's G Yang-Mills as the correct dimension. This has to have a 1 over m Planck in it. Okay, so we get the sort of obvious units for the coupling constants correctly. Another interesting thing to notice is these amplitudes have everything upstairs. They don't have any poles. But as been already commented, these amplitudes for Yang-Mills and gravity, exactly the exciting theories that from the Lagrangian point of view need gauge redundancy, blah, 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 blah. There's also something here. These 3 particle amplitudes have poles. That's weird. It's weird for a 3 particle amplitude to have a pole. Normally when amplitudes have poles, the pole means some propagation of some particle, you're supposed to factorize on the pole, something exciting happens with the poles. Here there's a pole already at 3 points, and that's quite mysterious and strange. It's forced on us, there's nothing we can do about it. The only consolation is that these amplitudes vanish in Minkowski space. So whatever the hell they're doing, whatever weirdo, slight non-locality they have about them, does not correspond to anything we can detect in Minkowski space. But it's some clue that there's something interesting and new about these guys relative to the more boring theories, like scalar theories and Yukawa theories. Along these lines, there are other interactions we wrote down. Why did I write down this fancy one with 2 minuses and a plus? Let me write down one with like all minus, let's say. Minus. Well, what is this guy? This guy is 1, 2, 2, 3, 3, 1. That's it. Right? But now, what are the units of this guy? Right? That's right. So this needs to have a 1 over mass squared in front of it. This is a higher dimension operator. Okay? By the way, which higher dimension operator is it? What do you think? Something like f mu nu cubed, right? Which has the correct units. All right, and similarly for gravity, minus for gravitons here, I can have 1, 2, 2, 3, 3, 1 squared. Okay, and this is a 1 over m to a higher power, whatever it is, 4. Okay, and this is an r cubed operator. Okay, so if you add an r cubed operator to the Lagrangian, you would get these interactions. So that's why we don't care about these at 0th order. They're much less important than these leading ones at low energies. Okay? And you also see that, let's say you had some other funny theory of massless spin 1 particles that for some reason didn't have these interactions, but it had these ones. These would not be exciting theories. I could trivially write down a theory that's not general relativity of an interacting massless spin 2 particle. I simply write all the interactions in terms of the linearized Riemann tensor, beginning with Riemann cubed. It's a totally stupid theory, nothing wrong with it, local Lagrangian, no big deal, no general covariance, just this stupid linearized gauge symmetry, nothing exciting, no long-range forces, and this would be its amplitude, and it's a polynomial. It's as boring as Yukawa theory and phi cube theory. Similarly, for a theory of interacting massless spin 1 particles built out of linearized f mu nu cubed. Okay? But it's exactly these theories where, from the Lagrangian point of view, we need covariant derivatives and gauge fields and all of that stuff, where we don't just make things out of trivial gauge invariants, where something exciting also happens from the perspective of the amplitude. Okay, so I'm just trying to connect this to things that you might be more familiar with. In principle, I don't need to say any of those things. We're just writing everything down completely determined by symmetries. Okay, any questions about this? So now we have written down all 3 particle amplitudes in principle for any spin. Sorry? Yeah, I mean, when I say away from Minkowski, I mean not in Minkowski signature. It's all flat space-time, but not in Minkowski signature. So this is valid for general complex momenta. Okay? Yes? Should the 4 be probably have to be a 5. Riemann cubed. Riemann cubed? R is, yeah. No, R is... exercise for the reader. Okay. All right. Okay. So that's all for pure kinematics. Now we're going to talk about dynamics. And it's going to be the 4-particle test and factorization. Okay. Yes?
Just to summarize, so in Minkowski space, all of these 3-point amplitudes vanish.
Except the case where,
scalar.
yes, except for the scalar, that's right. And all the other ones where h1 plus h2 plus h3 is 0, purely kinematically, they can also be there and they're non-vanishing, although they look funny. They look like 0 over 0 in Minkowski space. As you go to Minkowski space, that's what looks funny about them, right? When h1 plus h2 plus h3 is 0, they look like 0 over 0. But exactly those guys that are 0, 0 end up being ruled out by this 4-particle test. Okay? So the only ones that end up being physically relevant are the ones that we talked about, and they all vanish in Minkowski space, other than the phi cubed. By the way, that's what's so special about the Higgs self-coupling. Okay, so there's all kinds of things about what a 100 TeV collider might do. I'll talk about it a little bit in my colloquium tomorrow. But one beautiful thing is it's the only particle that can have a non-trivial 3-particle amplitude in Minkowski space. Nothing else in the world does. It's the simplest possible interaction in the world. Only the Higgs can enjoy it. And so it's a very interesting thing to try to measure it. It has a lot of course, important information in it otherwise. Okay, so now we want to talk about 4-particle scattering. And I'm going to make an assumption of weak coupling here. Which means that I'm going to work in an approximation where the scattering amplitude only has poles. Now, if you were doing Feynman diagrams and Lagrangians, then that's clearly what you mean by tree level. Okay? What we mean by tree level from this on-shot perspective is slightly different. Of course, they're very closely related. But you can say it in an invariant way that has nothing to do with the underlying Feynman diagrams, is that the expansion we're talking about instead of the loop expansion is an expansion in how complicated the functions are. And the simplest possible thing is that they don't have any poles at all. They're just some contact interaction, a constant, s squared, s cubed. So I'm talking about 4-particle amplitudes. What are those? Those, from a Lagrangian point of view, correspond to just higher dimension operators, or even the contact terms, phi to the 4, phi squared, box phi squared, and so on, right? So we can have, okay, so that's the absolute simplest possible thing. The next simplest thing, which has some interesting dynamics at low energies, is when the amplitude has poles. And when it has poles, we interpret it as the exchange of particles of some mass. And if the particles are massless, of course, the poles are sitting there at st and u equal to 0. Okay? Now, the real amplitudes also have branch cuts, and they have more interesting structure beyond that. But the expansion in weak coupling, or the loop expansion in terms of Feynman diagrams, is slightly more invariantly an expansion in how complicated the analytic structure of the amplitudes is. So we're going to make the assumption of the simplest possible analytic structure of just having poles to begin with. Okay, it's a huge program in this subject to try to figure out ab initio as much as possible, but even peeking at the answer as what Feynman diagrams look like, it's a very deep and rich and difficult subject to figure out what the analytic structure of the amplitudes is actually supposed to be at some general loop order, never mind non-perturbatively. Okay? The answer is known to one loop in any theory in any number of dimensions, but 2 loops is the frontier today. Okay? So it's remarkable that in the early 21st century we don't have the answer to such an incredibly basic physical question: what is the analytic structure of amplitudes of relevance to the real world, when we know the analog of the answer to this question for fancy schmancy things like conformal field theories. Okay? We don't have the answer to this question for physical things about the actual world, and I think that it's a wonderful problem to think about. But anyway, here we're not talking about any of those things. We're just talking about the simplest situation, which is the analog of tree level, where the amplitude only has poles. Yes?
When you organize things in loop expansion,
Yes?
you have divergences.
Yes?
What is the counterpart of this?
The counterpart of divergences is that you have is that there are discontinuities across cuts whose integral diverges logarithmically. So we can have there's a whole discussion about how to think about the RG from this point of view, which is not very well understood. I mean, it's mechanically understood, of course, trivially, but it's not conceptually as well understood.
It's the whole ideology of
yes.
Wilson that the
That's right.
divergence comes from.
Exactly. So this is what if you're around tonight, we could speak for hours about this subject. Okay, but just to say that the on-shell point of view and the Wilsonian point of view are conceptually as orthogonal as possible. Right. The Wilsonian point of view about effective field theory is about Euclidean quantum field theory. Okay? And the entire picture of dividing the world, the distance between short distances and long distances, is not something that even makes sense in Minkowski space. In fact, it's false in Minkowski space. There's no such thing as short distances which can't be light years apart close to the light cone. Okay? So the whole picture that we talk about, we wire it so much into our thinking, is not something that is actually applicable in Minkowski space. It's a Euclidean thing. Okay? And that's why the Wilsonian picture of the world is very powerful for certain questions, but is less powerful for others. And when we talk about amplitudes in a quantum field theory, in fairness, amplitudes are something that's kind of not a natural question for a local quantum field theory. Local quantum field theory is Euclidean. They love correlation functions in Euclidean space. You have to torture local quantum field theory to get it to produce scattering amplitudes as an answer. Okay? So maybe from that point of view, it's not so shocking that there should be some better way of getting the answer that doesn't force that torture. On the other hand, the question about the renormalization group is one where local quantum field theory does not need any torturing at all. It's very happy to give you the correct way of thinking about things, and that's a real challenge for the on-shell way of thinking about things. But mechanically, it's just there's a cut. The divergence, the discontinuity across the cut is the log that comes from the particle production, and it just happens to just keep on going, so that when you integrate it, you get a log.
Not physical interpretation.
Not the same physical interpretation at all. Of course not. There's no zooming out gradually, integrating out off-shell modes. That's both deeply virtual, deeply off-shell, deeply Euclidean, completely orthogonal to the on-shell way of thinking about the world. Yes?
Maybe I got it wrong, but we can take this format and reproduce somehow the RG flow, and we can go to fixed point. Then we can suppose we have a CFT. Is there any connection between the helicity and the scaling dimension of the particle?
Well, if we have a CFT, none of this is applicable. There are no scattering particle states in a CFT. So we're not talking about CFTs.
Yeah, but I still have correlators.
You have correlators, yeah. There's some way of interpreting correlation functions as the scattering amplitudes for certain massive particles that are the proxy for the local operators whose correlations you were measuring. But it's definitely not what we're talking about. Okay? We're talking about real world things, your photons, electrons, gravity, actual real stuff in the real world. So that, yes?
What about infrared divergences?
Infrared divergences are very important. They're definitely there. We're not talking about them yet. Okay? So, absolutely, yes. So infrared divergence. So everything that involves the words, everything that happens at long distances involving emission of particles, physical, actual, dynamical processes are things that have to be captured by this way of thinking about things. Absolutely. Okay, but you guys are asking much more sophisticated questions. So we're just going back now here to try to understand something very basic. But this is the exercise we're about to go through is also quite deep, because by the end of this exercise we'll understand why nature at long distances has to be described by some theory of gravity coupled to some Yang-Mills theory, potentially with supersymmetry, and that's it. Okay, and that's going to be a consequence of pure thought, beginning with the principles of relativity and quantum mechanics. Okay, so that's what we're about to see momentarily. All right, but what is it that we're doing? Well, we want to find some amplitude, some 2 to 2 amplitude. The assumption is that it only has poles when S or T or U goes to 0. But on those poles, let's say as S goes to 0, being a little schematic here, but we'll see what we mean exactly in examples. On those poles, let's say as S goes to 0, I have to get the product of 2 3-particle amplitudes summed over whoever can propagate there. And whoever can propagate there, maybe there's some particle species I, maybe it has a helicity H. This is I on this side, it would have helicity minus H. See, it has to be H and minus H on this side, because we're imagining all particles are incoming. So if all particles are incoming, the one that propagates from here to there, if it's incoming here with H, it'll be outgoing here with H, incoming with negative H. Another way of saying it is that, a more obvious way of saying it is that whatever this is, it should not know anything about the little group of the internal guy, because the amplitude knows nothing about the little group of the internal guy. So we have to have an H on this side and a minus H on this side for the little group weights to cancel between them. Okay? So as S goes to 0, we have to get, as S goes to 0, we have to get 1 over S multiplied by this. Similarly for T and U. Okay, that's it. You see, from here already, you see, we're almost getting kind of a quadratic equation. Because we know, we're going to get some interesting constraints, because we know what these 3-particle amplitudes are. We've just determined them. And so there's some constraint that whatever 4-particle thing we write has to have the sort of correct poles. Now, on the face of it, this looks totally trivial. So let's do the simplest example of this, just again with the scalar theory. Okay, so let's just say we have our phi cube theory. What is the 3-particle amplitude? Well, it's just G. So here's an obvious strategy. The obvious strategy, all I'm trying to do is build a function of ST and U that has poles at ST and U goes to 0 with some residue. So let's first work out what those residues have to be. So what is the residue? In this case, I have to glue together. So let's say the residue is S goes to 0. I have to glue together these 2 amplitudes. It's very simple in this case. Just multiply this by this, and I just get G squared. Right? So that's the residue. And so how do I build a function that has the correct poles? Well, the amplitude could be G squared over S plus G squared over T plus G squared over U. Right? Now that's something which, by construction, has the correct poles as ST and U goes to 0. Now, I don't know this is the whole amplitude because there are contact terms. There are polynomials in S and T, or ST and U, doesn't matter. These I can't determine like this, right? And again, that's fine. From the Lagrangian, if I tell you there's a phi cubed coupling, maybe there's also a phi to the 4 coupling. Maybe there are other couplings too, right? So I can't determine the entire amplitude simply telling you there's a phi cubed term. I can determine the part that has the poles though. Okay, or said more invariantly, I can determine that the amplitude looks like this up to contact terms. And then I can, if I tell you more about the theory, like in the ultraviolet, the amplitudes die like 1 over S, then that's tantamount to saying there's no phi to the 4 term. If I say that, then I tell you all these polynomials are not there. And so from now on, I'm not going to bother keep writing down plus polynomials over and over again. All we're going to do is attempt to write down objects that factorize correctly on all the poles.
Sorry, how do
Okay?
we know we have simple poles?
Sorry?
How do we know the order of the poles?
Oh, the fact that we have simple poles is where we're inputting. Thank you. I was just going to summarize this. So we assume locality / causality is the statement that we have poles as ST and U goes to 0, and they're only simple poles. Okay, that's related in the Lagrangian. It's related to the fact that we have a 2-derivative kinetic term. Incidentally, locality, causality, and unitarity are very closely tied to each other. This is a point Matt was making earlier today as well. So there's also difficulties with unitarity if you have higher poles. Okay? But the sort of clean thing to say is that causality and Lorentz invariants tell you that the structure of the poles is simple poles in S, ST, and U. Unitarity tells you they have to factorize on the poles into the product of 2 lower amplitudes. Okay, so that's so let me say this again. So locality / causality is the statement that there are simple poles as STU go to 0. Unitarity is what tells you that you have to have factorization on those poles. And we can spend longer talking about talking about this and a few related things, but let me defer the discussion for the people who are interested in hearing it later. Okay.
Just
Yes.
a different question. Just how do you know that they're all g squared and not 2g squared in one of them?
Oh, because the residue, we know what the residue's got to be is the factorization. It tells us it's this times that, and that's g squared. Okay.
Oh, in all of them it has to be.
Yeah.
Okay.
So that's the assumption. This is our 3-particle amplitude. We computed the residue, and it's the same. Yeah. So it's the same residue for all of them. Okay. Yes. Sure. Yeah. To lunch. Yeah. That's yeah. All right. So let me then do one example, and then we'll have to pick up the rest of it afterwards. But just. By the way, exactly the same thing happens for Yukawa theory. There is nothing funny going on in Yukawa theory. But something funny is happening in those theories where the 3-particle amplitudes had poles. You see, in those theories, you should be scared, because even the 3-particle amplitudes have poles. So when you compute the residue that you get in the S channel, it's not obvious that that thing itself doesn't have poles. And in fact, it will. So let's just see it. All right? So let's say we have a single, I'll just do this example and we'll stop. A single particle, massless particle, of spin capital S, just so I don't confuse it with the S. All right, and the amplitude that I'm going to put in, my basic 3-particle amplitude is the one that we talked about, this one and its friend. So 1, 2 cubed over 1, 3, 2, 3 to the power of S, capital S. Now let me look at now let me attempt the same exercise. I'm going to try to see what is the residue in the S channel. Okay? So I'm going to look at an amplitude. I'm going to look at the amplitude 1 minus 2 plus 3 minus 4 plus. And then the residue in the S channel, here it is, 1 minus 2 plus. And this is some intermediate guy that I'll say is minus. And here's the intermediate guy is going to be plus on the other side, 3 minus and 4 plus. So let's first compute this residue. So what is the residue? Well, I have to just multiply these two things. So there's some g here. So I'm going to get g squared. Residue is g squared. On this side, I'm going to have I'm going to have 1i cubed over 1 I cubed over 1 2 I2. And on the other side, I'm going to have I4 cubed over I3 4 3. And all to the power of capital S. Okay?
Shouldn't the one of them be to the minus?
Hmm?
The square brackets are not to the minuses?
No, because this is the opposite helicity configuration. See, here it's minus, minus, plus, and here it's plus, plus, minus. Okay? All right, well, we can simplify this. So now, I have to get rid of the dependence on I here. Okay, but that's quite easy because you see here I get lambda I and the lambda tilde I. So let's look at this expression. So if I look at 1I, for example, 1I, I4, this is 1, then the momentum for particle I and 4. But the momentum for particle I is like P1 plus P2, let's say, times 4. And P1 times 1 is 0, because P1 is lambda lambda tilde. So this is the same as 1 P2 4. Okay, so this is like 1, 2, 2, 4. So you can do that manipulation for this guy. You can do a similar manipulation for this guy. And let me just write down the answer. It's just 2 lines of algebra. So the answer is that the residue in the S channel is equal to G squared multiplied by 1 3 squared angle 2 4 squared square divided by U to the power of capital S. See, it's not surprising that you're going to get a U downstairs because, for instance, when I solve for the I downstairs, I can get the 1 I have here I have an I2, I3, so I could solve for PI as P1 plus P2. Then here I'd get a 1 2 1 3. That 1 3 is like a U. Okay? Okay, so that's the residue as S goes to 0, and you see it's scary because the residue as S goes to 0 has a pole in U. Okay? So now let's see so in other words, now it's not obvious that all I have to do is take the residue and multiply by 1 over S, and then the residue in the T was 1 over T, and so on. That's not obviously going to work because even the residue is a pole in the other channel, so it might not work. Well, let's see if we can actually do it. Let me begin. Obviously, if S equals 0, everything is okay. We did that already. Let me do S equals 1. Okay, if S equals 1, we see the residue as S goes to 0 looks like 1 over U. All right, so that means that what the amplitude has to look like is some A. I don't know what they are. The amplitude has got to look like. Let me factor out this 1 3 squared 2 4 squared. But there's got to be some A over SU plus B over UT plus C over ST. That's what it has to look like, right? All right, so now this is scary because I have these funny double poles downstairs, but let's see if it has a chance of working. So what is the residue of this M as S goes to 0? Now notice as S goes to 0, I can get a pole, well, from this term as well as from that term. And remember, as S goes to 0, we have S plus T plus U equals 0. So as S goes to 0, T is actually equal to minus U. Okay? So the residue as S goes to 0 of this is equal to this factor. I'm not going to keep writing down, so divided by the factor. This is equal to 1 over U times A minus C. Okay? So that's good. I got the 1 over u. I was supposed to get the 1 over u. This is A minus C. But then I have the similar formula for the T and the U channels. Right? So I conclude from here that I have to have A minus C is equal to G squared. I have to have C minus B equals G squared. And I have to have B minus A equals G squared. From matching all the poles. Now I have a small problem that if I sum these equations, I get 0 equals 3G squared. Okay, so this theory is inconsistent. So we discovered there's no such thing as a self-interacting massless spin 1 particle. A single one. And indeed there is not. Okay? And it's a good thing there isn't, because if you look at that 3-particle amplitude, it has the wrong Bose statistics. There's a lot of bad things about it. Right? Now let's just stick with this thing in a second before going on to higher spin. What if we had many of these particles? Let's say we had many of these particles, not just one of them. So now the amplitude is exactly the same, but let's say there's a bunch of them, A1, A2, A3, same amplitude. So the 3-particle amplitude, I'm now just going to say G, and I'm just giving this coupling a name. I'm just calling it F, A1, A2, A3. This is just a name. Okay? And now it's multiplied by the same thing, 1, 2 cubed over 1, 3, 2, 3. Okay? Now, none of the argument changes. I have some amplitude. A1, A2, A3, A4, which would equal some capital A, A1, A2, A3, A4. I just add these indices to everyone over SU plus B, blah, blah, over UT plus C over ST. All right? And now the residue, what is the residue in the S channel? Sorry, multiplied by, again, this is over this 1, 3 squared, 2, 4 squared. The same thing as before. Now the residue in the S channel is exactly what it was before. It's 1 over U, 1, 3 squared, 2, 4 squared. But now, now I just have to sum. I have some A1, A2, intermediate I, A3, A4. So the residue in the S channel is F, A1, A2I, Fi, A3, A4. Okay? So now I have to have a new consistency condition. Now it's the same as before. Now I have to have that A minus C, A1 through A4, A1 through A4. This has to equal F, A1, A2I, Fi, A3, A4. Now the same thing for C minus B and B minus A. Similarly have to equal FF and FF. And now these equations do have a solution, or they can have a solution, if and only if, when you sum these 3 terms, you get 0. That's the Jacobi identity. So that's how we discover that if you have massless spin 1 particles, the only consistent theory of massless spin 1 particles has to have the coupling constant given by the structure constants of a Lie group. Okay? Again, to pure thought, Lorentz invariants, locality and unitarity imply the only possible consistent theories of massless spin 1 particles have the Yang-Mills structure. Okay, let's return to a single particle, and then I'll stop. We'll do a few more examples next time before we switch to talking about the analog in cosmology.
Is it obvious that they should be antisymmetric?
Yes, yes. It's obvious from a variety of points of view. The quickest thing is that that's the only thing that guarantees the correct Bose statistics. Now you can ask where we get the Bose statistics from, and we can derive the spin statistics connection in this way as well. Okay, but everything that you see in spin statistics, Kalman-Weinberg, Weinberg-Witten, every one of the basic things about field theory are a consequence of this algebraic consequence of this 4-particle test. Okay? We won't do all of them, but okay. So let's do S equals 2. Okay, now this is a little cooler. So if you have s equals 2, now the residue in the s channel is 1 3 to the 4th, 2 4 to the 4th over u squared. Now we're surely screwed, right? Now it's 1 over u squared. There's a double pole there. I'm just screwed. But remember that as s goes to 0, t equals minus u. So this is only true as s goes to 0. So this could also equally be, as s goes to 0, negative 1 3 to the 4th, 2 4 to the 4th over tu. And therefore, there's a unique expression that gives me the right answer. Minus 1 3 to the 4th, 2 4 to the 4th over STU. That's the gravity amplitude. Okay? So now, attempt to calculate this 2 to 2 gravity amplitude from the Lagrangian. And unless your name is Bryce DeWitt, forget it. Okay? So even the 3-point Feynman rule, I don't know, it's 50 terms, and the Donder gauge is some horrendous horror, right? But we just wrote down the answer. Okay. What if we go to even higher spin? Then we're just dead, right? If we go to even higher spin, then it's 1 over u cubed, and then we're screwed onto the Lord, because there's no expression with only simple poles in st and u that can possibly give us that answer. Okay, so we conclude there are no such thing as self-interacting theories of massless particles of spin higher than 2. Okay? Now, in the, by the way, this minus sign is why gravity is attractive. I mean, you get really everything. Yes? Yes. Yes. Yes, in fact, so here we're talking about the amplitude for a single massless spin 2 particle. Well, we'll do some of this next time. I don't want to, it's important. I don't want to fly through it now. This is just one of them, but to begin with tomorrow, we'll talk about other things that can interact with these guys. So if you take other things that can interact with these guys, you'll discover, let's say, anything that interacts with the massless spin 1 guys has to be in a representation of the Lie group. Anything that interacts with the spin 2 guy has to have a universal coupling to it, and the coupling is the same as the self-coupling that it has. If the spins are bigger than 3 halves for coupled to Yang-Mills, or bigger than 5 halves for coupled to gravity, they're simply inconsistent. You can't do it at all. You can't have more than one massless spin 2 particle. Okay? You can only have one of them, and its couplings are universal. Every one of those things is a consequence of this little quadratic equation. Okay? And you see it's a quadratic consistency condition precisely for these interesting theories where the 3 particle amplitudes have poles in them already, so that when you go to do the 4 particle test, there is a non-trivial constraint because the residues in one channel force the existence of poles in other channels. Okay?
Sorry, how about the anomaly?
This is all tree-level stuff, and so all the issues about anomalies show up later. Okay? So anyway, let me just leave this. I think this is just to give you a taste for what these consistent conditions look like. Next time, I will review a few more of them. Just so the last one is that we'll just go. I told you that particles of spin greater than or equal to 5 halves are simply inconsistent if there's any gravity at all. Particles of spin, if there's gravity with its normal gravitational self-interaction, I mean, you can't have any particles of spin 5 halves or higher. You can only have one spin 2. What about spin 3 halves? No problem. You're allowed to have massless spin 3 halves. Okay? So that's fine. Nothing wrong with having a massless spin 3 half particle coupled to gravity. But what if you want to have a theory with a massless spin 3 half particle and just one scalar, say? Okay, well, nothing wrong with that, and you have gravity. Well, what happens is if you now look at the 2 to 2 amplitude of the scalar and the spin 3 halves guy, there's some 2 to 2 amplitude mediated where there's some t-channel pole here coming from the graviton. You discover, if you glue these together, that the residue in the t-channel has a pole in the s-channel. Okay? And now you're kind of dead, you think. You have a pole in the s-channel, what could I possibly have in the s-channel? In the s-channel, I have a scalar and a fermion. What can I have in the s-channel? Well, you can have a partner, a fermionic partner. Okay? So if you have a massless fermion that's a partner to the scalar, In fact, you're forced to have that. And then you can have a consistently scattering, you can have a consistent amplitude. So that's supersymmetry. The only way you can have consistent theories of massless spin 3 half particles, if you just have one of them, it's fine. You don't need anything else. But any matter, the matter has to come in multiplets of supersymmetry. Okay? And this is n equals 1 supergravity. Then you keep going. You say, can I have 2 massless spin 3 half particles? Nope. Sorry. You have to complete it into an n equals 2 gravity multiplet. And so on. So you discover supersymmetry. Again, no imagination, just this one dumb consistency condition. You discover you can't have more than 8 of these massless spin 3 half particles. And of course, at 8, you've hit n equals 8 supergravity. And that's it. There's a finite list of the possible consistent theories of the world from interacting massless particles. And that list is arrived at from these simple consistency conditions. All right, so I'll review a little bit of that next time. I'll talk about what happens for massive particles, and then we'll at least sketch out what the analog of all of this is for cosmology. Okay, thanks a lot.